In this video we're going to consider one application of using matrices, and this is called Leslie matrices. These matrices are named after a guy called Patrick Leslie who was studying population growth and population change. And the thing that Leslie matrices allow us to do is to use matrix multiplication to consider population change in age-specific groupings. So Leslie matrices use matrix multiplication to model population change in age-specific groups. Well, what does that mean? Well, think about, for example, a human population, and let's say that people live from 0 to a maximum normally of 100 years. Well, rather than just going what's the rate at which the population as a whole is growing or declining, we might instead choose to break that up into age-specific groupings. So we might sort of say, well, let's use 10-year groupings and down to 90 to 100, because the significant thing there is that the rate at which population is growing or changing is quite different in those different age groups. And the two things specifically that are quite different in those age groups are going to be the birth rates and the survival rates. And that's the two ways that population grows, if you like, by, in this case, people being born or people surviving from one age group to the next. So, for example, we would say in, the years maybe, 0 to 60 or something like that, we would say survival rates are very high. Most people in the age group 0 to 10 survive to be in the age group 10 to 20 years old, and so on. When it comes to birth rates, that's a little bit different. It would probably be more in the age groups 20 to 40. That's where birth rates are the highest. So it's people between the ages of 20 and 40 who are contributing most to adding to the number in the population. So the two factors which are considered are birth rates and survival rates. And sometimes survival rates can be expressed sort of in the complementary way, in the negative way, saying death rates. And so then we just need to say, well, the survival rate in a particular age group is just kind of 1 minus the death rate, or 100% minus the percentage death rate. So how do we use those? Well, let's consider an example. And to maybe simplify it, rather than sort of taking 10-year age brackets, let's just consider 1-year sort of age groupings. So let's say a population of snakes Now I'm going to use some figures here from one of the worked examples in the textbook, so that's where these numbers come from, but there's no context there, so I've just said let's choose the context to be snakes. So a population of snakes has the following we'll call them characteristics. And just to make it nice and simple, we'll say, to make it nice and simple, we'll say there's only 3 age groups. So age groups are 0 to 3, sorry, not 0 to 3. Let's go 0 to 1, so there's snakes that are 0 to 1 year old, 1 to 2 years old, and then 2 to 3 years old. And so we're assuming that sort of beyond that, no snakes live beyond that age. So birth rate, survival rate. And so the figures that we'll choose in here will say, well, no snakes in that age group produce. 2.3 is a birth rate there, 0.4. Like I say, I've just grabbed these figures from one of the examples. 0.6, 0.3 and 0. Okay, so what do each of those things mean? Well, the birth rate here, and basically with Leslie matrices, for all of our rates and our numbers, we use female numbers because obviously they're the ones who produce offspring. So the age-specific birth rates, let me just provide a quick definition for those. And there it is there. So the birth rate numbers are the age-specific birth rates, which is the number of female offspring produced by a female in this age group. Now, because we're talking 1 year age brackets, we can read the 2.3, for example, as each female in the 1 to 2 year age group on average produces 2.3 female snakes or female offspring per year. Okay, so it's all per year. Then we've got the survival rates. So the definition for survival rates is as follows. The age-specific survival rate is the proportion of each age group which survives to the next age group. So we can read the 0.6 survival rate, this one here, as saying that 0.6 or 60% of 0 to 1 year old snakes survive to be 1 to 2 year old snakes. And that's why we have a 0 in that last place there, because in our model here we're saying 0% or 0 proportion of the 2 to 3 year old snakes survive to be 3 to 4. So 3 is the sort of oldest, the upper limit of the age groups. Now what we can do then is actually use matrices to model these. So our Leslie matrix, and we'll use an L, capital L for our Leslie matrix. What we do is put our birth rates along the top row of that. So 0, 2.3, and 0.4. And then our survival rates start in the next position. So we go down to the next row, and our survival rate for the first age group goes there. Then we put zeros in the remainder of those places. Then down on the next row we start with a 0, and then our next survival rate goes in the next spot, and then a 0. So those survival rates, it may be a little bit hard to see the pattern because it's such a small Leslie matrix, but they're going diagonally down from the sort of row 2, position 1. Okay, so birth rates along the top, and then survival rates starting in that row 2, column 1, and going diagonally down. Now, we'll see why that works. So let's also choose an initial population, age-specific population. We'll call that P0. And what we'll find is that it doesn't actually really matter what we put here, but let's just put even numbers. So in the example I'm borrowing from, they put 800 in each of those age groups. And this is the initial age-specific female population. So what that's saying is, initially at time 0 when we start this model, there are 800 female snakes in the 0 to 1, 800 in the 1 to 2, and 800 in the 2 to 3. So what happens then if we multiply the Leslie matrix by the initial population matrix? Well, what we'll do is we'll actually get the population 1 year later. So if I go L times P0, so let's go 0, 2.3, 0.4, 0.600, 0.30. So I just want you to see the sort of mechanics of what actually happens here when we multiply that by that. Obviously there's quite a few zeros in there, but we multiply row 1 times the column matrix times the population matrix. We're going to get 0 times 800 plus 2.3 times 800 plus 0.4 times 800. Now let's think about that for a moment. So what that's going to give us is after 1 year, this row here, those calculations represent basically the number of new snakes that have been born during that year. So after 1 year, that's going to tell us the number of snakes that are now in the 0 to 1 age group. And they all come from new births. So there's 0 births from the first age group because the birth rate there is 0. But for each of these 800 female snakes that were 1 to 2 years old, they each produce on average 2.3 female snakes during that time. And for each of the 800 snakes that were in the 2 to 3 age group, they on average each produce 0.4 female snakes during that time. So that's where all the snakes in that 0 to 1 age group are going to come. Then we've got in the next row 0.6 times 800 plus 0 plus 0. Then we've got a 0 plus 0.3 times 800 plus 0. Alright, so each of those, let's give the figures for each of those. So that's 2160. The next one is 480. And the last one there, 0.3 times 800 is 240. And looking at those numbers there, again, what they represent is saying, well, from the new births, we've now got 2,160 new sort of female snakes in the 0 to 1 age group. From the ones that survived, so from the 0 to 1 year olds that survived, 60% of them survived. There's now 480 snakes in that age group. And of the 800 female snakes that were 1 to 2 years old, 0.3 of them survived. So there's 240 that are now in that age group. And obviously the 800 snakes that were in the 2 to 3 age bracket, some of them have produced offspring, but none of them have survived. So there's kind of 0 down here in this next age bracket. Alright, now I realize this video has already gone for a while, but we need to think a little bit more about what sort of happens over the long term. So we can keep going with that same process. So I could say, after 2 years, the age-specific female population is going to be L times P1. So basically use these numbers now as my population, multiply them by the Leslie matrix again, and we'll find the female population, age-specific population in each of those age brackets again after 1 year. And so we can sort of keep doing that for, for a few iterations. And so let's actually say, in general, let me write one line before I do in general, and that is to say that would also be L times P naught, because that's how we calculated P1, wasn't it? So that would be L squared times P naught. Alright, so we can say that the population after 2 time periods, or 2 years, is going to be L squared times P naught. And so this is where I could say, well, in general, the population after n years, or n time periods, is going to be L to the power of n times P naught. And so you could do that using your calculator. So let's go down and actually sort of analyze this for the first number of time periods. So using this, and on your calculator just define the L matrix and the P matrix, and then keep multiplying this. We get the following figures for, let's say, the first 5 years. Alright, so grab your graphics calculator and actually have a go at doing this for 5 iterations and see if you get the following numbers. And that was our initial setup there. So we had per age group at time period 1 or at the start 800 in each age group, and then using our matrix multiplication on our calculator, we're going to do L times P to get the first one, and then do L times that answer to get the second one, and so on. And these are the figures that we should get. There's the figures that I get for those first 5 years, doing them as, so these are female age specific population numbers in each of those groups. Now if we wanted to get the total, obviously the initial one there's pretty easy, so rather than having to go through and add those up each time, we could do that using a matrix calculation. So you've defined your L matrix, you've defined your P matrix on your calculator. Now we've got 3 age groups here. If we also define an S matrix, which we'll just use for summing these up, and because we've got 3 age groups, we'll just use a 1 by 3 matrix, so it's got 1 row and 3 columns which are all 1s. And if you do S times L times, well, let's say P naught as the first one, then basically you've already done your, or you know what happens with your L times P naught. So basically you're going to be multiplying that S by your P1, which is going to be your 2160, 480, 240. And if you think about what that matrix operation does, it multiplies this row times this column, and it gives you a 1 by 1 matrix, which is just going to be the sum of each of those, which in this case I think is 2880. So if you went through, multiplied that that S matrix by each of these, then we would get each of these ones added up. So this one's 4147.2. Let's go with 3850.6, and this one here 5913.2. Alright, so that S matrix there allows us to add up each of those. Now, as you look at those values there, I want you to notice a few things, and that is that, firstly, that there is some pretty wild fluctuations going on there. If you look at the total population, it's quite clear that over those 5 years, it is neither uniformly increasing or decreasing. It goes up in the first one, but then it comes down after that. It goes up, then down, then up. It does seem that the general trend is upwards. Certainly it seems to be that generally it is increasing, although there's some changes. And even within age-specific groupings, so look within the 0 to 1 age groups, you can see there's a massive increase, then a significant decrease, big increase, big decrease, big increase. So there's some pretty major fluctuations going on within age groups as well as overall. However, if we were to consider that trend over a much longer period of time, then what we would find is that actually this does level out to a sort of uniform growth rate. So over time, the growth rate becomes constant. Now we could sort of find that algebraically, and then we'd be getting into an area sort of called eigenvalues and eigenvectors. But we don't need to do that. We can just do it numerically rather than algebraically. And so, for example, we could consider what's the population after 100 years, 100 time periods. And we could go 500, we could go 50. We'd probably find that it's constant after that. Now, I'm going to do this as my total population or total female population. So I would on my calculator be going S times L to the power of 100 times the initial population. Okay, so S times L to the power of 100 times P, and that's going to give me, my calculator tells me, a population 1.7547 E, or 1E11. So in other words, times 10 to the power of 11. If I then considered the population after 101 time periods, I would get 2.11283 times 10 to the power of 11. And after another time period, so I'm just basically considering 3 successive time periods here that are, way down the track. Now, because each of those is times 10 to the power of 11, I don't really need to use all of those figures in my calculation. But what I want here is, what is the growth rate between successive time periods? So basically I'm going to say take 2.11283, divide it by 1.75471, and that's giving me a figure of roughly 1.2. Okay, so about 20% growth. And if I do the same thing for this one here, so take the larger one, or the second one rather, divide it by the one before it, which was 2.11283. Alright, so what that's suggesting to me is when I get certainly this far down the track, that growth rate seems to have leveled out. So the long-term growth rate is approximately 1.2, or we can say 20% per year. Alright, so it does level out to something, and like I say, we could have maybe tried it with 20, 21, 22, or 50, 51, 52, and what we'll find is that maybe even after 50 iterations that this has leveled out to a constant growth rate. The last thing to say just before finishing up here, and I know this has been a really long video, is that if we changing the values in P0, so if we change those values in P0, and maybe we'd still say, well, overall there's 2,400 snakes, female snakes initially, but let's change the proportions, and we could even change it to be 2,400 if we wanted, and just check what impact that has. What we'd find is that really that has no impact on the long-term growth rate. Obviously the initial values, like the ones in the table I've got there, would be quite different for the first 5 years, but by the time we got to P100, 101, 102, even though the numbers might be different, the rate would be the same. It would be 1.2. So changing the values in P0 has no effect on the long-term growth rate. And by all means, experiment with this if you like. Pick some different values in P0. The long-term growth rate would still be 1.0. So long-term growth rate is dependent on L and not on P0. So in other words, it's dependent on the survival rates and the birth rates, not on the initial population numbers. Alright, that's enough for this video. Well done if you've made it to the end.